So today we are going to do the gravitational field. So what are fields? All right, so before that, what is gravity? So we have learned about gravity. So gravity is something that is offered by Earth on any particle. So if a particle has a mass of m and we know that the gravitational acceleration is in the downwards direction, and as a result of the acceleration, there would be a force acting down, and we call this a force due to the gravity. And the magnitude of the force due to the gravity is mg. It is simply because F equals to ma, right? If I apply F equals to ma in the downwards direction, the only force that is acting on the object is the force due to the gravity, and that is equals to mass. Then the acceleration in the downwards direction is mg. So we get the force of gravity as mass times the gravity, right? Newton discovered this gravitational acceleration, and he defined an equation, Newton's law of gravity. Okay, so Newton discovered this force of gravity. So he mentioned that as long as there are two masses at a separation of r from each other, and one of the mass is m1, the other mass is m2, he mentioned that there would be an attractive force between those two masses, right? So we will have this and this. And he said that the attraction force is proportional to the multiplication of the masses themselves, and it is inversely proportional to 1 over the radius square value. So he combined both of those equations, and he got it is proportional to m1, m2 divided by r square. And we know that we can change the the proportionality constant to an equal sign by inserting a constant, and that constant is g. So we call it g m1, m2 over r squared. So this g is what we call the universal gravitational constant, right? So it is called universal gravitational constant. (6.67 times 10 to the power of minus 11 Newton meter squared per kilogram squared, right? So that would be the value of g, right? So this is pretty much what gravitational force in between two masses would be, right? Please take this down. And right, so this is force due to the gravity. So now imagine that you have a mass and you have another mass, simple m. One is capital M, the other one is simple m. And as per the Newton's law of gravity, we know that there is going to be a force acting in between them, and they are equal and opposite because of Newton's third law. And if they are at a separation of r, then we say that the force that is in between those two particles as the force due to the gravity, and that is of magnitude gmm over r squared. So we learned that as long as there is a force acting on an object, which is the net force, of course, then that particle will be accelerating in the direction of the force. So if I just consider this particle alone, and if I apply F equals to ma in the direction of the force, which is to the left, the only force that is there is force due to the gravity. So let's call them Fg. So force due to the gravity, and the mass of the particle itself is m, and acceleration is a. So we know the force due to the gravity is this. So we can say that is G capital M simple m over r squared equals to ma. And we can say this as the acceleration due to gravity. So acceleration due to gravity is g m over r squared, right? So that is this equation. And this acceleration due to gravity is due to the mass capital M, all right, at a distance of r. So we can say this is the acceleration due to gravity of mass m at a distance or from the center. So we know that the universal acceleration is 6.67 times 10 to the power minus 11, right? And it is Newton per kilogram squared per meter squared. So imagine that we have a table, and we do have a lot of objects, right? We have our laptop, we have our mouse, we have our teacup or whatsoever, and we have tons of things on our table. So if there exists a force between these objects, then of course this laptop will be attracted by the mouse, and the mouse will be attracted by the cup, and the mouse will be attracted by the laptop itself. Meanwhile, if I have a light lamp or something, that would be attracted by the laptop, and this would be attracted by the light lamp, and the mouse will be attracted by, and everywhere or in between each and every mass, there would be a force due to the gravity. So what is the reason why none of these objects are not at all moving? Because there exists a force in a particular direction, and that is the net force. Imagine that this table is frictionless. Maybe you can assume that this is coated with oil, so there is no friction at all. So there is no restitution force. So if there exists a force, then these objects should be moving towards each other. So why they are not moving is because of this magnitude. So look at this magnitude. This is 10 to the power of negative 11. So what would be the weight or mass of the laptop? It might be around 5 kilogram. Maybe the lampshade would be 20 kilogram. The mouse would be around 200 grams, not even kilograms. Cup would be another 300 grams whatsoever. So imagine that if we take these two objects, which is 20 kilogram and 50 kilogram, and if we do the math to find the force in between them, that would be 6.67 times 10 to the power of minus 11, 20 times 5 divided by, let's say they are at a separation of 1 meters, the distance between them, then it is going to be 6.67 times 10 to the power of minus 9 newtons. So this is a really, really, really small number. It is nearly equal to 0, right? Because 10 to the power minus 9 is 0.000. You have to stack 8 zeros, and at the end you will have 1, right? So that is nearly equal to 0. So this is the reason why on Earth objects are not attracted to each other. Otherwise, each and every object will attract other object, and they should be moving, or they should be in motion, right? So usually we will use these concepts for planets, right? The reason why we will use it for planets is because the mass of Sun, if I have to give you a value, mass of Sun is 1.989 times 10 to the power of 30 kilogram, right? So this is 10 to the power of 30 means that you have 30 zeros. And mass of Earth is 5.97 times 10 to the power of 24 kilograms, right? So that is the mass of Earth. So imagine, comparative to the mass of the laptop and the mass of this one, even if you take a train, that would be a couple of tons, or not a couple of tons, maybe 10 tons or 50 tons. Even if you take a huge ship, that would be around few thousand or few hundred tons, right? Which is 10 to the power of 9, right? So comparative to this 10 to the power of 9, or maybe even 10 to the power of 10, this 10 to the power of 30 and 10 to the power of 24 are huge values. So the sun and the earth would have considerable attractive force in between them, right? So understand why this theory is not applicable for normal objects on Earth, right? So we will usually go for anything in between planets or extraterrestrials. Right. So we went over the concept of force, the concept of acceleration due to gravity, and why these forces doesn't exist in Earth environment. And then we will look at some variations, force and acceleration. So we know that the force due to the gravity between two particles is given by gmm over r squared, and the acceleration due to one of the mass at a particular distance r from the center of the mass is gm over r squared. So in math, you would have learned that y equals to 1 over x squared is a graph that looks like this, right? So we will be using that in this concept. So let's say that I have a planet, maybe the Earth itself, or sun, or whatever the planet, and I have an axis that goes through the center of the planet, right? And these are the radius of the planets, okay? And the acceleration due to gravity of that planet at a distance r. So this is y, which is my force, and that is my x, which is the center, the distance from the center. So this is my planet's radius, so say capital R. So at a distance capital R, the acceleration due to gravity would be gm over capital R squared. It is not equal to 0. It has a value, right? So let's say that this is that value, right? Gm over capital R squared. So it is not force. We are drawing for the acceleration, okay? So gm over capital R squared. And we know that from the math, we learned that it is an inverse squared relationship. So the graph will come like this. And since it is a vector quantity, we will have the opposite direction as the negative. So that is going to be minus gm over r squared. And this is going to be the value, and we'll have a graph like this, right? But for your additional information, that inside the Earth also, we will have gravitational acceleration, which is not in your syllabus though. But just to know, the variation inside the Earth will be a straight line, and it has a equation as well. Why not? So the equation for this would be gmr over r cube, right? But remember that this is not in your syllabus, and you wouldn't need it at any given point, right? So based on this graph, what you can find out is, let's say at a distance of, I don't know, maybe 2r, if I ask you what is the force, what you can do is, if you are given a graph, you can come and find this value, and you can multiply this value by the mass that you place at that position. So let's say simple note, and you have a value, let's say that as capital A or simple A, then the force acting, or the force that is going to act due to the gravity of this mass on that object would be m naught A, right? But let's do the question from the beginning. So we have the mass of the mass of the Jupiter, which is 1.9 times 10 to the power of 27, and we have the radius of it. And the first thing is find the acceleration due to gravity on the surface. So we have the Jupiter, we have the radius here, capital R, we have the mass, and acceleration due to gravity is given by g m over r squared. G is 6.67 times 10 to the power minus 11. Time mass of the Jupiter is 1.9 times 10 to the power of 27 divided by the radius, which is the distance from the center of mass, right? Which is 7.15 times 10 to the power 7, because we are looking at the surface. So you square this. So the answer would be simple calculations. 24.79 Newton per kilogram. So compare this value to the one that we have on the Earth, right? So what is the acceleration due to gravity on the Earth? It is nearly 10. It is the same thing, right? But it is 2.5 times that on the Earth, right? Always, whenever you get an answer, please compare the values and try and get some understanding of what they are. So the second question is, find the force of gravity on an object of mass 4 kilogram that is kept on the surface. So we are going to apply F equals to ma. So basically what they are asking you is find the force due to the gravity of on a mass of 4 kilograms. So it is nothing but mass times the acceleration due to the gravity, which is 4 times 24.79. So it is 24.79 times 4, which is 99.16 Newton, right? So the third one is find the force on an object of mass 4 kilogram that is kept at a distance twice that of the radius. So now imagine that what we can do is we can consider the Jupiter as a point. So that is the Jupiter, right? So that is your Jupiter. And now you are keeping another mass of 4 kilogram at a particular distance, right? So the distance to that mass to the Jupiter is twice that of the radius. So what is the radius? 7.15. Twice that of the radius is 14.3 times 10 to the power of 7. And we are looking at the force acting on that mass. So it is force due to the gravity. We have to apply the other equation, gmm over r squared. It is 6.67 times 10 to the power of minus 11 time mass of the Jupiter is 1.9 times 10 to the power of 27 times mass of the other object is 4 divided by the radius, which is 14.3 times 10 to the power of 7 whole thing square. So the force due to the gravity that we have in between these masses is given by this equation, which is 6.67 times 10 to the power of 11 times 1.9 times 10 to the power of 27 times 4 divided by 14.3 times 10 to the power of 7 square. So we have an answer which is quite wrong. Give me a minute. Okay, so we have 24.7. Why am I having the same answer? What is wrong? What is wrong? What is wrong? Okay, you get the same answer for some reason. Why my answer is the same? Oh, my bad. This is force, that is acceleration. My bad, my bad. I'm sorry. All right. So this is the force, right? So earlier, the force was this. Now the force is this, right? I was looking at this and I was like, okay, why am I having the same answer? That is the acceleration. This is the force, right? So there is another easier way to find this one instead of going over the equation. So what we know so far is the Jupiter, and at the radius, the force is what? 99.16. So the force that is acting on that object is 99.16 Newton. And now what we have done is we have doubled the distance to the mass and the center of the Jupiter. So now question is, what is that force? So if I look at the equation, which is gmm over r squared, we can use the proportionality, F proportional to 1 over r squared, because the numerator, the values in the numerator are all constant for the first scenario, this one, and the second scenario, this one. So for the first one, it is 99.16, and it is at a distance of r squared. I consider the r as the, what do you call r as the, sorry, all right, so I'm going to consider r as the radius of the Earth, right? So using this proportionality, what we can do is we can say that it is 99.16, which is the force proportional to 1 over r squared. And the other force is proportional to 1 over 2r whole thing squared, which is proportional to 1 over 4r squared. So what is the understanding here, or what we can do is we can do using the math itself. So we can go for second divided by the first equation. So I would get force divided by 99.16. And it is force, and we have 4r squared here, and we have r squared there. So I can cancel the r squareds. So the force is going to be 1/4 of the initial, right? So 99.16 divided by 4 is 24.79 newtons, right? So that is the force. So what is the relationship? If we double the distance, right, the force becomes 1/4, or we can say 1/2 square, right? So that is this inverse squared relationship, right? Motions of the satellite. So the next thing we have is satellite motion. So when we were doing kinematics, we went over the rotational motion, and one of the main condition that has to be there for any particle to be in a rotational motion is there should be a force towards the center of the rotation, which we call this a centripetal force, right? It should be mandatory for any object performing a rotational motion. The value or the magnitude of the centripetal force is given by the mass of this object and the radius from the axis of rotation. And we call this mv squared over r, where v being the velocity of the rotation, right? And we also can do v equals to r omega, the conversion of linear parameters to rotational motion parameters, and we can substitute this and we can get this equation as mr omega squared, right? So these are the two equations that are related to the force or centripetal force, which is a mandatory requirement for any object to be in a rotational motion. So imagine if we have our sun, if we take the solar system as an example, we have the sun and we have the earth. Let's omit all the other planets. And earth is revolving sun with a particular velocity, right? And we know that there exists a force between these two masses because of the Newton's law of gravity. And we know that magnitude. And we know that there is a distance between the sun and the earth, right? So using all of these parameters, what we can write or what we can determine is the force due to the gravity, which is obvious. So let's say mass of the sun, this is mass of the earth. So that is G mass of the sun, mass of the earth divided by R square. I'm going to use capital R because it is the distance between the earth and the sun. So I'm going to use capital R square, right? It is not a general R. So that is the force due to the gravity. And then we can consider this as a single unit, and we can apply F equals to ma towards the center. And it is performing a circular motion. It is not a circular motion in actual case because it is an orbital motion. But for simplicity, if we take it as a circular motion, then the force towards the center of the motion is force due to the gravity itself, and the mass of the Earth is me, and the acceleration that should be there in order for any object to be in a rotational motion is the acceleration or centripetal acceleration. So we can say the mass of the Earth, acceleration, centripetal acceleration is v squared over r, which again is capital R because the distance from the rotational center is r, and force due to the gravity is g ms me over r squared. So we can cancel this me, and we can cancel the r. And what we can find out is the velocity of rotation, which is going to be g ms over r and the square root. Right? So this is a generalized equation, but you don't have to memorize this equation, but you should be able to determine this equation by doing a quick calculation like this. So this is a required velocity for the Earth in order to perform a circular motion about the sun at the radius, which is the distance between the sun and the earth, right? It is a similar concept for any satellite as well. So if we expand this concept, but having earth as the center because satellites revolve around the earth and we have satellite, I'm going to use simple ms for satellite. Okay, so that is my satellite. And the radius from the center of the earth, all the distances that we are going to be using in this gravitational acceleration, gravitational field and electric field are going to be the distance from the center. So let's call that r simple s, right? And we can use this same equation to figure out the velocity with which the satellite should revolve around the earth to be at the radius rs, which is given by vs. I'm going to say it is actually v naught. I will explain what that naught is given by g mass of the earth me and the radius at which the satellite is revolving the Earth, right? And we call this velocity as the orbital velocity. So that is the orbital velocity, right? So the generalized equation for the orbital velocity is this. So that is your orbital velocity. For any planet, if you want to find out the orbital velocity of an object around the planet at a distance r is given by this equation, okay? So it is not the orbital velocity of Earth around the sun. And here, orbital velocity of the satellite around the Earth, right? Take this down and let me know. So now we are going to learn something about geosynchronous satellite, or as in like Sri Lankan syllabus, we call it geostationary satellite, right? Both of the terms refer the same thing. So what is it? So we have the Earth, right? In addition to the motion or the rotation it has about the sun, we know that Earth has its own axis and Earth rotates about its own axis, and the period of rotation is 24 hours, right? So every 24 hours, the Earth is in rotation. So we know that for any broadcast or internet or any telecommunication to work, we have the telecommunication satellites. So the satellites will be there on space, right? At different locations. I'm just only using 4 satellites, but you have tons of them, right? So let's say that is the Asia, you have the Russia, you have Australia, you have Africa, you have North America, South America, Antarctica, and Arctic. So at a given point, if there is a satellite, say S1, right above the Sri Lanka or maybe Australia, let's say. So right, so let's say it is 12 o'clock in the afternoon. Right above that Australia, we have a satellite, okay? And we know that this Australia will not be here after a while. So after 1 hour, let's say the Australia is here, but if this satellite is somewhere here at 1 hour, right? So it has to be right above the Australia, but if it is for some reason, if it is somewhere away from Australia, then the signals that are sent from the satellite will not be able to be received by the receivers in Australia. So what should have been done is the satellite should have moved with the Australia, right? So wherever Australia goes, the satellite should be right above it. So what that means is the satellite also should revolve around the axis of the Earth with a period of revolution of 24 hours. Does that make sense? So this is what we call the geostationary satellite. So geo means Earth, stationary means at any given point, if you look above, there will be a satellite, and that satellite will be there forever. Any time of the day you look above, that would be the same satellite you looked earlier, right? So that is what we call geosynchronous satellite or geostationary satellite. For geostationary satellite, the period of rotation would be 24 hours. So that is what we call period of rotation is 24 hours. So we know that if we know the period of rotation, we can find the velocity and stuff like that. So let's say that geostationary satellites are at a radius of r. And we call this simple r naught, right? And the mass of the satellite is ms, mass of the Earth is capital Me. So what we can do is we can apply F equals to ma for the satellite towards the center, and we have the force due to the gravity acting on the satellite due to the mass of the Earth, and we have the mass of the satellite. And acceleration is centripetal acceleration. We have velocity v squared over r naught. So force due to the gravity between those two objects going to be me ms R naught squared is ms v squared over R naught. We can cancel this. And we will end up with a relationship GME over R naught is V squared, and we can take the square root, but let's keep. So this is a very familiar equation to us. This is what we learned as orbital velocity. No difference, right? So why this is a special case is because we have a relationship between the velocity and the period of rotation. So what is it? So let me go to the next slide. I will come back to the previous slide. So the relationship between orbital velocity, orbital velocity and period of rotation, right? So T is the period of rotation, and at any given, at a radius of R naught, this is going to perform a rotation about the center. So the distance it would have traveled is 2 pi R naught, which is the circular circumference. So I can say the velocity is given by, it is this, let's call it speed, just to be consistent with the theory we learned earlier. So speed is distance divided by time. So the speed is the orbital speed. We call it orbital velocity, but we can interchangeably use the orbital velocity and the orbital speed in this particular chapter, because we are not interested in the direction, we are only interested in the magnitude. Okay, so that is the reason why the speed and velocity are interchangeably used in this particular chapter. Okay, so the distance it has traveled is 2 pi r naught, and the time period is t. So we can see that this t is 24 hours. It is strict, right? This is strictly 24 hours because it has to move with the at the same speed as the Earth rotates about its own axis. So if this is a constant and this 2 pi is also a constant, right? Then V naught is proportional to R naught. But if we go to the previous slide, what do we have? We have this relationship, right? What is it? So we have the orbital velocity to be equal to g m over R naught, and that is squared. So I can square this and say, okay, V naught squared is proportional to R naught squared. Is that possible to say? Yeah, it's possible. We will have a different um, constant, right? So that is possible. So I can substitute this and I can say, okay, maybe this is proportional to R naught square, proportional to Gm over R naught. So I would get R naught cube is proportional to Gm, which is a constant for a given planet, right? So R naught cube is proportional to Gm for a given planet. So what does that mean is there exists only one geostationary orbit. So that means you can have these telecommunication satellites, such as the broadcasting or telecasting or the internet sources. I'm not really very sure about the internet satellites or the satellites that are used for internet, but for broadcasting and telecommunication, the weather satellites, that is also one among these important geostationary satellites. You can have only an ample amount of satellites on the orbit because you only have a particular radius. It is very strict. You have a very unique radius at which the satellites can travel at the same speed as that of the Earth about its own axis. So that is why this geostationary satellite is such a unique topic, or it is a standalone topic, right? Right. So electric field is pretty similar concept as that of the gravitational field. Instead of the masses, we will have charges. So we know since childhood that we have learned same charges, so we call it like charges, repel each other, right? Opposite charges attract each other, right? But we haven't learned how about the forces in between those charges are going to be. So I will say I have a point charge, which is say Q1, and I do have another point charge, say Q2. And if they are at a distance of R, then a very similar equation to that of the force due to the gravity, we will have force due to the electric field, which is given by K Q1 E2 over R square. In gravity, we learned that the force due to the gravity is G M1 M2 over R square. Very similar in concept or in the form, right? So we call this universal gravitational constant. We call this electric field constant, right? So this K is actually 1 over 4 pi epsilon naught, right? So this is from Gauss's law that we will not learn in this syllabus. You do not have that. But this theory is from Gauss's law. So just know the names. Maybe in university, if you happen to learn these, you will figure this out. So that K is 9 times 10 to the power of 9. So here it is 6.67 times 10 to the power of minus 11. And here it is 9 times 10 to the power of 9, which is the K value. Okay, it is not the 4 pi epsilon naught value, it is the K value. Similar to that, we can find the acceleration due to the electric field at a given distance r from the center of a charge as kq over r square. It is also very similar equation to that of the gravitational field. Apart from what we learned in the gravitational field, in gravitational field also we have something called a gravitational potential, but since it is not in your syllabus, we are not going to go over that. But in electric field, we have something called electric potential, and we have something called electric potential energy, right? So this is a very, oh, I wouldn't say very familiar, but kind of a familiar concept, potential or potential energy. In kinematics, so in previous mechanics, when we were going over this, we went over something called potential energy, right? So what was it? So if I have a mass m, and if it is at a height of h from the ground level or zero potential level, whichever we define as zero potential level, we say the potential energy is mgh, right? So that is the potential energy, and we know that. So what is a potential? So potential is basically if I divide this potential energy by whatever the mass of the object, then that is what we call the potential, and the potential is given by capital V. It is not V, the velocity anymore, it is potential, right? Okay, so PE is here, B. So in this case, we have the charges. So let's say it is plus Q, and at a distance of R, what is the potential energy, right? So if I go back to the potential energy concept here, if you are given with a potential and if you multiply by the mass, what you are going to get is the potential energy, and this is your gravitational potential energy, right? So keep this in mind, as we'll be using the similar concept here. So if I have a plus Q charge and if I have a radius R, and if I ask you to find the potential at a given point, then that is given by minus K, sorry, not minus, KQ over R. So what is a potential? So potential is defined as the amount of energy that is required to bring a unit charge or unit positive charge from infinity to a radius r equal to 0. Let me write that down. So it is the amount of energy required to bring a unit positive charge from infinity to a radius r, right? So remember that the radius that we talk in terms in the fields are always from the center of the object. All right, it is not from the surface or anywhere. It's always from the center of gravity or center of the object. So what is happening at infinity? Because we are talking something in relation to infinity. So if I use the force due to the gravity, which is, oh, not force due to the gravity, force due to the electric field. It is the same thing for gravity and electric field. It is k q1 q2 r squared. If r squared goes to infinity, if r goes to infinity, r squared goes to infinity, force due to the electric field will become zero, right? So if I go back to the graph that I talked in gravitational field, you can see that as r goes to infinity, the force is becoming zero, right? It is force due to the gravity, but it is the same thing because the graph is the same thing, right? And also, it would be the same graph if you try and draw for force of electric field force or electric field strength. Okay, it would be the same graph. Where is it? Okay, here. So at infinity, we do not have any electric field force. So there is no influence of the plus q charge or minus q charge or whatever the charge that we are talking about at infinity. So if I am doing a work to bring a charge to a place here, so from r equals to infinity, so let's say this is r equals to infinity, that means there is no force. And if I have to do a work to bring a charge and keep it at r equal to r, or at a distance r from the center of the charge, then whatever the work that I am doing will be converted or will be stored as the potential energy in the charge itself, right? So that is the concept. So this is like we can do it using integration. So we can go from r equals to infinity to r equals to r, force due to the electric field times the distance, which is we can call it r or x, whatever. So r dr. Or maybe we will use, okay, well, don't worry about this. We are not going to do the integration, but this is the equation that is used to find the work. And using the work energy concepts, this work has to be either stored or taken away from the mass or the object that we are considering or talking about. So in this case, since I am doing a work, this work will be stored in the object. It is not always the case. Sometimes if you have the same charges, you have to do a work. But if they are unlike charges like positive and a negative charge, if you are bringing a negative charge in the vicinity of a positive charge, you don't have to do a work. In that case, it is going to be a negative work, right? So we learned what a negative work and positive work back when we were learning work and energy concepts. So in this case, we are doing a positive work because I am bringing a unit positive charge in the vicinity of a positive charge. So of course, the positive charge that is already in place will repel the positive charge that I'm bringing with me, right? So this work will be stored as the potential energy, right? So that is going to be stored as potential energy in the system. So we will say the potential energy is given by K Q over, right? And the potential is KQ over R. And don't forget that these are all scalar, right? These are all scalar quantities. So these are scalar quantities. They are no longer vector. Next thing we have is uniform electric plates. So uniform electric plates are two plates, right, that are parallel to each other. And what we are going to do is we are going to distribute positive charges to one place, and we are going to distribute negative charges to another plate. So we have positive charges on this plate, and we have negative charges on the other plate, and we have equal amount of positive and negative charges on both the plates. So based on the fundamentals, since we have positive and negative charges, they will attract each other. So we will have electric field lines going or generating from positive charges towards the negative charges. And since it is a parallel plate and we have equal number of positive and negative charges on opposite plates, we will have parallel and uniform electric field. So this is what we call electric field lines. So what is an electric field line? So we did not go over what is it. So electric field lines are the path, right? So are the paths through which a positive charge would travel. So that means in this case, if I have an electric field like this, and if I happen to place a positive charge in this area, then the direction of the motion of this positive charge will be in the same direction as that of the electric field that I have over there. And on the other case, if I have an electric field like that, and if I place a positive charge here, then that will come down along this line, right? If I have an electric field line that looks like this, then the positive charge will also move in the same direction and along the same path. So that is what we called an electric field line. So in this case, since it is a uniform electric field, we can call the electric field to be capital E. So that is the electric field intensity, right? So electric field intensity is pretty much the acceleration due to the electric charge that we keep. So in order to find the force that is acting on an electric field, because we understand that if I place a positive charge here and that is going to move from bottom to up, and why the charge is moving is because there exists a force acting on that charge. So if I want to find the electric field force that is acting on that charge, then what I have to do is I have to multiply the electric field intensity in this uniform electric field times the charge that I'm keeping it. So we will say it is F equals to EQ, right? So there are ways that we can find the electric field intensity using Gauss law. Once again, it is not in your syllabus, so don't worry about that. But know that we can find the E. But in most of the questions that you are going to deal with, you will be given with the E values, right? So that is your velocity. And if I say that the distance between these two plates is D, right? Then I can say that the electric field or electric potential between these two plates, right, is we can say it as dV by dx equals to E. So that is your calculus way of writing it. If not, I can write it as the electric field intensity is given by the potential difference across the plates divided by the distance itself, right? So that is the equation. So further down, you will learn something called capacitors, and capacitors are basically two plates that are kept at a distance d, and equal amount of charges are distributed on the plates itself. And we will have a uniform electric field, of course, in between those two plates, right? So, so that is what we call a capacitor, right? So we talked about projectile motions, right? So it is like we point something or we throw something with a particular velocity, and due to the gravitational field that is there, which is pulling the object downwards, this object will move something like this. Pretty much, if I have an electric field or electric plates such that the field lines are pointing downwards, right? And if I project a charge within this electric field with a particular velocity of v, right? So here, if the electric field lines are like that, then you should understand this is going to be positive charge and this is going to be negative charge, because electric field lines always generate from the positive charge and it ends up in the negative charge. So if I project a positive charge within this electric field, what is going to happen is the positive charge will be pushed down because the electric field lines tell you the direction of the motion of the particle. So they will move something like this, right? So very similar concept as in gravity, right? So we can calculate similar things that we have calculated in the projectile. So we have calculated the range, we have calculated the final velocity, we have calculated this distance, or maybe it is given. So let's find some parameters. So let's say this is D, and let's say the electric field intensity is uniform and of magnitude E, that is Q. So the first thing that I can find out is if that particle is within this electric field, then there would be a force acting in the downwards direction, very similar to the force due to the gravity. But in this case, it is force due to the electric field. And the force due to the electric field is given by EQ. And that is in this direction, right? So if that is EQ, then I can apply F equals to ma and find the acceleration in the downwards direction. So the only force that I have is force due to the electric field EQ, and the mass of that, if I say that as m, right? So mass would be m, and acceleration due to the electric field in the downwards direction is EQ over m. So this is coming down a distance d, and if I have projected in a horizontal velocity with a horizontal velocity, then I can apply delta y equals to VIT plus half AT squared in the downwards direction. And the distance that it is going to move, or the displacement, is going to be d, and the initial velocity in the downwards direction or vertical direction is 0 because I'm projecting in the horizontal direction, plus half. The acceleration is EQ over m. And you might ask, okay, wait a minute, where is the gravitational acceleration? Because we know gravitational acceleration exists everywhere. So we are going to assume that the gravitational acceleration is negligible when compared to the electric field intensity or the acceleration due to the electric field that we have in this place. So from this, I can find the time of flight. So time of flight is going to be 2 dm over EQ and the square root. So since I know the time of flight, I can find how far it has moved along the parallel plates and hit the bottom plate. I can use the same equation, but I'm going to use it in the horizontal direction or horizontal projection. So that is half AT squared horizontally. So the distance it has moved and hit the bottom plate is delta x. Horizontal velocity, the initial velocity is v. And we have 2 dm over EQ. And similar to the projectile motion in the gravity, we are saying that there exists no force in the horizontal direction because there is no force in the horizontal direction. So the acceleration in the horizontal direction is 0. So we can find the delta x, which is the distance where it hits the bottom plate, which is given by v square root of 2 dm over EQ, right? So don't memorize this equation by any means. These are not supposed to be memorized, right? But know how you can find the values that we are trying to figure it out, okay? Well, the next thing that we can find out is at this point, we know that horizontal velocity will be conserved, so that is b, but there should have been a vertical velocity, so let's call it vi, right? And if I want to find that what the final vertical velocity as it hits the bottom plate, I can use vf equals to vi plus at in the downwards direction. So the final velocity is vy, initial velocity in the vertical direction is 0, acceleration due to gravity is eq over m, and the time is 2d m over EQ and the square root. So that is square root of, I will have EQ or 2d EQ over m, I guess. So that is your final velocity, right? So we have the final velocity as this. And once you have the final velocity, you can take the square roots of the velocities v and the vy, and you would be able to figure out the final resultant velocity, which is this, right? So the final resultant velocity, let's see if I have a different color. Yes, so final VR, I don't have enough space to write it down, but VR is in by square root of v by square plus v squared.